You can stop anytime.
We have one more to come from the bathroom or wherever. Okay, 10:30. So let's start up again. I will make one follow-up answer to a question I had after the RT lecture. So when you're seeing these radiative transfer equations, it was always written at some wavelength lambda. And radiative transfer theory is always done basically one wavelength at a time. So I'm going to solve the equation, let's say starting at 350 nanometers, and I get the answer there. Then I solve it at 360 nanometers, and I get the answer there. Then 370, and all the way up to, let's say, 750. So when you do a hydrolyte run, and you say run from 350 to 750 nanometers by 5 nanometers, it's solving that equation at every wavelength. Now, and just basically starting from scratch, using the IOPs and the boundary conditions for that wavelength. Now, when you include a source term, like Raman scatter or fluorescence, so we're over at 600 nanometers, and I need to know the source term at 600. Well, that comes from light that's either been fluoresced or Raman scattered from the shorter wavelengths. So I start way off at a, say, blue or UV wavelength, solve it there, go to 410, 420, 430, 440. I know all those solutions. So then I can take those solutions and take the light field at, say, 430 times some fluorescence function that tells me how much light is fluoresced from 430 to 550, and then from 440 to 550, and 460 to 560. And that eventually builds up how much light is being stuck into the water at 550 from all the shorter wavelengths. So that's the way that's done. Okay, mathematical detail that you needn't trouble yourself with, but that's what happens. Okay, so we're now going to sort of shift into the second half of the class, which is remote sensing. So you've seen all the basics of optical oceanography in general, and now we start talking about ocean color remote sensing. Okay, so what we're going to do today is just talk about the basic terminology that's used in ocean color remote sensing, a few words about forward and inverse models, skip through this part about AOPs because you've already seen that a couple of times and you've made the measurements, so we don't have to spend much on it. And once again, you've already seen this business of how to estimate remote sensing reflectances, so we'll just kind of click through that as quickly as possible. And then the other kind of half of the lecture is to introduce this whole problem of atmospheric correction, which is really the central thing to doing ocean color remote sensing. And tomorrow there will be a lecture on how NASA solves the problem. And then if I give my final lecture on in the class on week 4, there will be a couple of other techniques for doing atmospheric correction. And so we start out here. There's a bunch of terms you'll see in the literature, and your remote sensing data get labeled by their spatial, spectral, radiometric, and temporal resolutions. So spatial resolution simply means what's the ground size of a pixel? And for an airborne system, that might be 1 meter. For something like CWIFs or MODIS, a pixel size might be a square kilometer at nadir viewing. So you'll see that number there. The spectral resolution refers to the number and width of the different wavelength bands that are being recorded. So MODIS, for example, is a multispectral system, and the bandwidths are typically sort of like 10 nanometers. A hyperspectral system might have 80 bands over the visible, and they might be 4 or 5 nanometers in width. Then the radiometric resolution refers to the number of discrete levels of radiation or light that you're able to distinguish. So in the old days, really old days, you might have had what's called an 8-bit sensor, meaning there's 2 to the 8 or 256 different levels that your digital sensor can measure. A lot of systems now are like 10 or 12 bit and up to a 14-bit sensor, which would be 2 to the 14th or 16,000 different levels that you can separate the incoming signal into. Or if you can think of those as different shades of a particular color, like red, green, or blue, that go from 0 at black to 1 at totally saturated with 16,000 levels in between. And then the temporal resolution refers to how often your sensor is going to fly over. So that's relevant if you're doing a time series. So you're looking at, effects of a hurricane on what's going on in the water. You'd like to have measurements maybe every hour, but to see what happened after the hurricane went past. And you could get that from an airborne sensor, or you could get that from a geostationary sensor that's looking down there and might be taking an image every few minutes. Or if it's MODIS or VIIRS, you might have to wait, at best once a day, you might get an image of the area. So then you'll also see, I've seen papers where they said, oh, we're doing 4H remote sensing. What is that? Well, I dig around. 4H means high spatial, high spectral, high signal to noise, and high temporal resolution. So just one of those buzzwords that everybody knows except me. So on the spectral resolution, you have monochromatic sensors, which means one very narrow wavelength. So if you're doing LiDAR bathymetry, you might be at 488 or 532 nanometers, but just one very narrow band, as opposed to panchromatic, which means you have one very broad band. So a black and white picture is panchromatic image, and you're probably detecting everything from like 400 to 700 nanometers. So a very broad system. And then multispectral, typically you have 5 or 10 wavelengths in the visible, and typically like 10 or 20 nanometers wide. So that's CWIFs, MODIS, VIIRS, those kinds of things. And then hyperspectral, you'll have 30 more or more bands with at least better than 10 nanometer resolution. Typically, a hyperspectral sensor will have 100 or so bands and maybe 4 or 5 nanometers resolution. So you'll see those terms around. Ken mentioned sampling interval and band width. So the band width is usually taken to be the full width at half max. And then the sampling interval is how far apart are these band maximum. So these are well-separated bands here. But as Ken mentioned, in a hyperspectral system or an instrument, they might tell you, oh, you have 2 nanometer resolution, but the bands are actually 5 nanometers wide. So you have bands that are separated by 1 or 2 nanometers, but there's a lot of overlap. So you're not really getting 2 nanometers, 3 nanometers, 4 nanometers. You're getting, 1 to 7 and 2 to 8 and 3 to 9 is what's really going into that number. So it's another one of those things that you have to understand to try to make sense of your data. Okay, then there's these data processing levels, and you'll just see a paper that says, we took the NASA level 1B data and we did our own whatever, and here's our chlorophylls. Well, the levels are, level 0 is the unprocessed instrument data at full resolution that's being measured by the satellite. So that could be volts or digital counts, whatever this instrument measures. And then the level 1A is they take that data and they apply the radiometric calibration coefficients that would convert volts or digital counts into a radiance. And they stick onto the file the information that allows you to georeference it. So the satellite just takes an image, and then you have to stick on the information that says, this is where the image was, where it was, the time of day, the direction it was looking, et cetera, et cetera. So that's the georeferencing parameters, but they're just stuck onto the file as metadata. They haven't yet been applied. And then level 1B is you take the raw data and the calibration coefficients and all of that, and you turn it into something like radiance units. And then once you've done that, you don't know what the level 0 data was anymore. You've now put out radiances, not volts or something. And so science really starts with the level 1B data. You've got radiances at the sensor, you know where it was looking and when the image was taken. Then atmospheric correction takes the level 1B data at the top of the atmosphere and gets you down to the sea surface. So then you end up with either something like the normalized water leaving radiance or reflectance at the sea surface, or products that are derived from that, such as chlorophyll and CDOM concentration, bottom depth, or whatever it is. But that's at the same spatial resolution as the level 1 data. So it could be, meter scale, or it could be kilometer scale, whatever. And then they take that data and they may map it onto a nice uniform latitude, longitude grid. Missing points will be maybe interpolated or flagged. And you kind of make these pretty pictures that you see on the NASA website that says, here's the whole world and here's the map of the chlorophyll. So that's level 3 data. A lot of us may want to work with this level 2 data. The more general, like public program manager types, they may want to say, just show me the map of the chlorophyll in the North Atlantic. And we don't care about any of this. And then there's kind of a level 4, which is if you take, let's say, the level 2 chlorophyll concentrations and CDOM absorption and so forth, and use that as input to a biogeochemical general circulation model, and then you put out some prediction of here's what's going on in the ocean because of climate change or the hurricane or whatever, then that's not variables measured by the instrument, but it's things derived from those variables. So that's the kind of highest level modeling. So you'll see those terms around. Then there's all kinds of models. So a model is just a representation of the real world that tries to maintain or keep the essential features of what's going on in nature, but get rid of the less important details. So that could be a physical model. If I wanted to model tides in Harpswell Sound, I could actually build me maybe a model of the coast of Maine, the size of this room, and I'd have water sloshing back and forth and all of that. And it would be a physical model of tides in Harpswell Sound. Or I could have a mathematical model that solves all the hydrodynamics equations and predicts it, given what's going on in the ocean, given the river inputs, given the wind and so forth. So models can either be physical or mathematical. They can be predictive models, which says, I'm going to predict something that I don't know from something that I do know. So you know the IOPs, you put them into hydrolight and it predicts the light field, versus a diagnostic model, which says, I have some data and I'm going to fit a curve through it and come up with some little model that I can then predict whatever from my best fit data. That's the diagnostic model. There's direct and forward. So a direct model, you would take IOPs, solve the radiative transfer equation, get out remote sensing reflectance. An inverse model, you take remote sensing reflectance, do something to that, and get back the IOPs or the chlorophyll. So direct and inverse. There's approximate analytical models, which are like the single scattering solution or Gerson's law. There's exact numerical models like hydrolight or Monte Carlo. And exact doesn't necessarily mean it puts out the right answer. It means that you didn't do a lot of approximations like assuming just single scattering or assuming homogeneous water or whatever. But that's the terminology. And then there's deterministic versus probabilistic. So next week, we'll talk about Monte Carlo solutions, which are probabilistic. They have statistical noise in the answer, and hydrolyte, for example, and a lot of other techniques don't use statistics. They're not statistical models. They don't have any statistical noise. Okay, so the way to view a forward problem is you really have fundamental information like particle index of refraction, particle size distribution, absorption spectra, but those things don't appear in the radiative transfer equation. There's no particle size distribution in the RTE. What's there are absorbing and scattering coefficients and volume scattering functions. So those IOPs basically parameterize in a convenient way things like particle size, shape, and so forth. And that's what's in the radiative transfer equation. So you take that plus boundary conditions, so how much light's coming in from the sky, what's the bottom reflectance. You run it through a very complicated math model, Monte Carlo, hydrolyte, whatever, and you get out the radiance distribution. And from that, you can then compute anything else you want, irradiances, reflectances, and so on. So this is a solved problem. If you give me these inputs and they're perfectly accurate, I can give you a perfectly accurate radiance distribution. Okay, the inverse problem is a little harder, and remote sensing is an inverse problem. So there we have some measure of the light field. We don't know the IOPs, we don't know the chlorophyll, we don't know the bottom depth. And in general, inverse problems may not have a unique solution. There could be, let me give you an example. Let's say I measure a remote sensing reflectance and it's green. So it peaks in the green and goes down in the blue and the red. Now, I don't know, was that a remote sensing reflectance from high chlorophyll green water, or was it clear water with a seagrass bed at 5 meters? They're both green spectra. So then I don't, just looking at that, may not have information that I can tell the difference in high chlorophyll green water and clear water with a green bottom. So that's what I mean by may not have a unique solution. So to solve an inverse problem and get the right solution, you usually either have to have some kind of constraints on the solution that would eliminate the wrong answer. So maybe I know the water is infinitely deep, so therefore it can't be clear water with a green seagrass bottom. And then I'll get the solution that says, oh, it's high chlorophyll water. Or you solve for only limited information. If all you have is RRS, maybe all you can get out is the ratio of backscattering to absorption. And so you always have to worry about non-uniqueness when you're doing remote sensing. We'll see some examples. So here's from the PhD dissertation in one of the ex-students of this class, Eric Rame, and he had gliders where he had measurements of LU and ED on a glider that went out and ran around Puget Sound, getting these profiles. So then what he does in his modeling, he has two numbers, LU and ED, and he would like to get back the absorption and the backscatter coefficients. So there's hope there. You have 2 bits of information, you can solve for 2 things. So here he's done a bunch of simulations with hydrolyte. And so there's a range. So here's ED at 490 nanometers was 0.547 watts per square meter. And in the simulations, there's a range of absorption and backscatter values that give him that answer. Then he has, actually, this is ED here, gives him this ED. And the width of the line is because there's little errors in the measurements. Then he has LU measurements. Here's LU and here's ED, sorry. So he knows LU, which is the blue curve. So there's a range of absorption and backscattering values that would all give him the same LU that he measured. And there's a range of values that give him the same ED that he measured. But the only place where both of those are satisfied is right here at this absorption and that absorption. So he's done an inverse problem where he took his ED and LU measurements at these two, or at 490, and then was able to figure out, here's the absorption by particulate and dissolved substance, and here's the backscatter coefficient at 490. And over here it's at 650. So that's his inverse problem. It worked quite well, and he got a nice paper too and a PhD out of it. Suppose now he says, well, this is great. Now I'd like to solve for absorption plus backscatter plus total scatter, for example. Well, now we got a problem. We want to get three numbers and we only have two pieces of information. So here, if you actually plot these results of these simulations on a 3D plot, absorption, backscatter, and total scatter, there's a line here where for this point here, you can run back and forth and you basically have any value of the total scatter here from 0.2 up to 0.8 would all give you the same A and BB. So there's no way to pick which point along here was the correct total scattering. Well, the reason that happens is remote sensing reflectance, but it depends basically on BB over A, and what the total scattering was doesn't really matter. So then if you want to actually figure out, well, somewhere along here was the total scattering, I need to come up with a third bit of information, a third optical measurement or whatever. Well, here's the way you could do that. If you knew the beam attenuation coefficient, then that would come in and you would say, oh, this is the point that has the correct B value so that B plus absorption equals the beam attenuation that I measured. So you've now added some new information. You have three bits of information. You can retrieve three numbers. So that's the way the whole is. Say again? Anyway, that's the way the whole inverse business works, is you're always trying to figure out how to pin down a unique solution when you may have many, many different mathematical solutions or physical solutions. So a way to view remote sensing then is you have things like imperfect atmospheric corrections. You may not know the boundary conditions like water depth. You have incomplete light measurements. Maybe all you know is remote sensing reflectance. And then you have what might be a very simple mathematical model like a band ratio. Then you'll get back chlorophyll or bottom depth, whatever, but you may have to put some constraints on making sure you get the right answer. And then you come out with what I'll emphasize is an estimate of what you want, like IOPs or chlorophyll. But you're never quite guaranteed absolutely that you really got the right answer, because you may have had some non-uniqueness thing going on that you haven't accounted for. Okay, so I've already talked about explicit models. Gerson's law, it's a nice little formula. You plug in these irradiances, you get back absorption. That's an explicit inverse model. An implicit model means you solve a forward model and you do it a lot of times and hope that, so let's say you run hydrolyte, you guess the absorption and scattering of the chlorophyll or the bottom depth or whatever. You run hydrolyte, you predict remote sensing reflectance. Well, that's too big. Okay, so then you go back, you run hydrolyte and you tweak the inputs and you do another run. Well, now the remote sensing reflectance is too small. So, okay, you go back, you correct the inputs again, and you run a hydrolyte again, and now it's a little bit closer. So you do a series of forward models with some intelligent way of changing the inputs from one run to the next and hope that that then converges and you finally get a solution that makes sense. So those are implicit models, or often just called iterative solutions. Okay, we've seen the remote sensing reflectance business. Yeah, Ben.
Implicit solutions seem fairly risky. That you might just kind of make an assumption, and how can you alleviate that risk?
Well, the way I keep it in mind is if I've got a simple formula, it's explicit. If I have to solve a bunch of forward problems, then it's implicit. And then the catch, of course, is figuring out when I solve the forward problem and I get the wrong answer, what inputs do I change to get a better answer the second time around? And that's the hard part. And there are, of course, a lot of fancy mathematical techniques that will look at your solutions and say, oh, you need to change this by 10% and leave that part alone. And those get fancy names like Levenberg, Marquardt, and gradient, steepest gradient methods and all that. That's what they're doing. And that's what Eric Rame did here, was he actually embedded hydrolite inside MATLAB's Levenberg Marquardt solution and let it tweak the inputs until he got the unique solution he wanted. So, okay. Not to dwell on this too much, we've talked about AOPs in previous lectures. We've talked about remote sensing reflectance and all of that. We talked about how remote sensing reflectance is a really good AOP because it depends only weakly on the external environment. Here's wind speeds and sun angles and sky conditions, but it depends strongly on things like chlorophyll or absorption or whatever we're interested in. And then you guys are now the masters of how you get water leaving radiance, so I don't need to go into that too much. You went out on the lab, you measured the sky, you looked down at the water, you put the plaque in here, and you know, here's this business of what angles to look at. Well, you've already seen all of that, both from Ken and in the lab, so I won't say too much about that. And here you put in your gray card, and then you're measuring this reflected radiance, and from that, you're trying to figure out what was the downwelling planar radiance that I need to use to divide into LW. But I did get a good question on that the other day. People were asking, well, if I assume the radiance is isotropic, ED comes from integrating radiance over 2 pi steradians, so why isn't this a 2 pi there? Well, if we assume the gray card is a Lambertian reflector, that means the reflected radiance is the same in all directions. So now let's compute ED for a reflected radiance here that's isotropic. So here's our definition of ED. It's radiance times cosine times element of solid angle integrated over all the downwelling directions. So that's our actually in this case, we're looking at upwelling radiance. So if the radiance is constant, independent of direction, that's just the L gray card value. That's constant, we can pull it out front. The phi integration then, nothing in here anymore depends on phi. So that just gives us 2 pi. And then we're left with the integral of cosine theta sine theta d theta from 0 to pi over 2. Well, the integral of this is sine theta, and then d sine theta is cosine theta d theta. So this thing here is just 1/2 sine squared theta integrated from 0 to pi over 2 to pi over 2. Sine at pi over 2 is 1, minus sine at 0 is 0. So we have this 1/2 here because the differential of 1/2 sine squared, that's 2 sine theta cosine theta. So that's where that half comes from. And that goes out, and you end up with the planar radiance is pi times the radiance if the radiance is isotropic. So that's where that factor of pi came from that you guys were using. So here's the deal. Suppose I want to get the scalar radiance for an isotropic radiance distribution. Well, then it's the same equation, but there's no cosine. So then you end up, you go through, there's no cosine here. You end up with the sine, which integrates to minus cosine. And then that ends up eventually giving you 4 pi times g is what the scalar radiance is. So you can work through the math, but that's where that stuff comes from. It's not simple. I mean, it's not complicated after you've seen it the first time, but it's very confusing before you've kind of gone through this kind of calculation and then say, oh yeah, now I understand. Okay, so then you did the measurement of getting the gray card reflectance. Now, this equation, I'm assuming the card's 100% reflecting, but really it's some reflectance, so we have to account for that. And then there's this pi ED thing, and you solve this for ED given the measurement of the radiance. So you know how that works now. And then you have to come up with this magic rho factor to figure out how much of this sky reflected light to subtract out. And you finally end up with remote sensing reflectance if you made a good guess here. So this whole business of where do you get this rho value all goes back to this class about 20 years ago when people were saying, well, okay, where do I get the rho value? And the answer is, well, you know, use 0.02 or use 0.03 or whatever. And that was it. So I went home after the class, did a whole bunch of simulations for different viewing directions and different wind speeds and different sun angles and all of that, and put together a table of rho values that you can actually look up the wind speed, the viewing direction, sun angle, and all of those, and get a better value of rho. And those have been used probably far more than they should have, but because they were just pretty simple simulations. But what I did was things like, here's a wind speed of 10 meters per second and a sun angle of 20 degrees, 30, 40, 60. And then here's a sun angle of 30 and different wind speeds, 15, 10, 5, 2. Well, what I found was that simply that if you're looking, for example, if the sun is straight overhead and you're looking down, you're going to get a lot of specular reflection. Just blows you away. Now, if the sun's out at 60 degrees, the specular reflection is going to go off in that direction, and you're not going to see much even looking straight down. So that's what you see out here. So I'm looking straight down, I'm looking at a viewing angle of 40 degrees, and if the surface were perfectly level, you get the dashed line, which is the Fresnel reflectance. Well, it just kind of turned out that for the sun angles where you usually do remote sensing, which is the sun is at like 30, 40, 50 degrees, that you get a minimum here when the viewing angle is, 30 degrees, 40 degrees, something there. If the sun is too high in the sky, you're just out of luck. Or for a sun angle like 30 degrees, as the wind speed comes up, you get more and more tilt on the wave facets, so you end up getting more and more specular reflection. But here's a 10 degree or 10 meter per second wind, here's 5. So typical ocean conditions, maybe 5 to 10 meters per second. The global average ocean wind speed is like 6 meters a second. Well, there, once again, a viewing angle of 40 degrees or so is kind of where you're in the minimum between specular reflection and reflection coming off the sky and so forth. So, okay, 30 or 40 degrees works pretty well. And then I looked at, if the sun's here, well, off here, I look towards the sun, Of course, I get a lot of specular reflection. So these are super big values. If I look directly away, that would be in principle ideal, but then I'm looking at my shadow. So that messes things up. So there's a kind of big, broad minimum that if you're looking at maybe 135 or so from the sun's direction, you're out here where there's the least variability in the rho values or the conditions. If you look at 90 degrees, you're kind of on the edge of this steep gradient. So you can get a little too much over here and the value should have been bigger than you used. So I just did some plots like this. This is for 5 meters per second. And it would say looking off in this direction, here's the contour of this 0.03 for rho, here's 0.04. So something like maybe 0.028 would be a decent value. And then you go to a different wind speed, you get some different value, maybe it's 0.04, so on. So that's where all of that stuff came from. And that was all done independent of wavelength. And then Zhongping Li comes along and says, well, you know, really this stuff all does depend on wavelength, you know. So he wrote some papers on creating wavelength dependence rho values, and you can go read his paper. And Zhongping Li gets really high credit with me because he never starts with what's already there and says, oh, well, I'll tweak that a little bit. He goes back and says, let's start from scratch. You know, we really need to not just like modify Kurt's things a little bit. We ought to go back to the start and really do this and look at wavelength dependence from the very first. And he's done that in a number of papers and come up with really nice stuff by just saying, we need to re-examine the whole problem from the very beginning. Okay, so, and then here's his technique. You know, instead of making a measurement above the surface and then having to remove the surface reflected light, Zhongping says, well, let's put a little shield on our instrument, stick this in the water. The shield will block the surface reflected light, and we get an actual measurement of water leaving radiance. And I know at least some of you are doing that. You didn't do this in the lab, did you? Okay. Yeah. The last class, we actually had one of these and you can compare it. But in a sense, now that it's been done, you say, well, that's really obvious. But if it's so obvious, how come nobody did it 20 years ago? Now, the downside, of course, is if you're on the deck of a ship 5 meters above the water, you can't really do that. But we're out here, it works great.
Well, there's other issues as well. I mean, two things about it. First is that the Japanese scientists you study more and make more energy studies. Secondly, the session has to stay dry. So if you're in waters where there's lots of stuff going on, it's hard to keep it dry and not falling into the water. So it works really well in calm water like here, but it might not work as well. The third issue is correction for shape. You have this thing on you need to correct for light that does not make it good or otherwise. And we'd love to, I mean, we have everything, all the hardware to do it, because it's stuck for the last 2 months. It's on a sheet coming to the US. Hopefully the next class.
Okay, so then a number of people have tried to develop techniques to estimate water leaving radiance from below surface measurements. And I think you did some profiles here of getting LU in the water, and then you have to figure out how to extrapolate that above the surface. Or if you've got a TSRB, you're starting with a number at 0.6 meters, and then what happens to that LU between 0.6 meters and the surface. And of course, what happens depends on what IOPs are in the water, and it's going to depend on wavelength. So that introduces a whole new bunch of problems. So as I just said here, you can measure LU or ED in the water, and you can come up with a ratio. It's basically remote sensing reflectance, except it's in the water, and you can try to extrapolate that upward. You can try to extrapolate an LU upward and get it through the surface and get an LW, and then you have an ED measurement above the surface. Well, maybe you can pull that off, but like Emmanuel said, you get self-shading. You need to know the water IOPs in order to compute the KLU. But if you knew the water IOPs, you probably wouldn't have to do this anyway. You'd already know what you were after. So this is another example of Mobley's law of conservation of misery. You know, there's just no way, it doesn't matter how you do it, there's problems. And then Howard Gordon did a bunch of stuff with the self-shading simulation. So here's the instrument here, which might be, you know, something here, but anyway, here's the instrument, and it's casting a shadow into the water. But when you make an LU measurement, you're looking through that shadow at the very start, and that's where your strongest signal's coming from. So you're not really looking at the ocean, you're looking at a shadow and then some ocean. And so Howard did all these simulations and found out that what really matters is the radius of your instrument and the absorption coefficient. So here's a plot of A times R. That product is what determines how serious the shadow is. So if you see there's a very low absorption coefficient or a very small instrument, then you get very little error due to self-shading. But let's just pick AR here as 0.1. So I can have an A of 1 and a radius of an instrument of 10 centimeters. Well, then come up to 0.1 and bingo, 25% error due to self-shading. If I had an instrument that was, I don't know, this big around and a higher absorption coefficient at that particular wavelength, so AR is 1, now I'm looking at 75% error just due to self-shading. So once again, people have done a lot of simulations of particular instruments now to figure out how bad is the self-shading as a function of instrument size and absorption coefficient in the output.
So if you're in the open ocean, you're not as worried, maybe not as worried about this.
Not as worried, because at least at blue or green wavelengths, the absorption coefficient is probably smaller, but than it is out here. But then again, if you've got your instrument, maybe your instrument's small, but it's on this big package, and you know that thing swings around between the sun and you know whatever. So.
And this is assuming this is like far away from the boat. Like,
yeah.
It's like off the dock side.
Yeah, and of course, you know, well, you don't want to lower your instrument on the shady side of the boat, or then you've got this like 10-meter sized instrument, which is the boat. You're totally messed up. So you lower it on the sunny side. Oh, well, then you've got light reflected off the side of the boat. So you want to get the instrument way away from the boat. So that's when you bring me in. I bring my collapsible kayak. I take your instrument, I paddle it off like 100 yards away from the boat. You take your data and then you retrieve it. Yeah.
Do you still have to worry about self-shading effects when that solar moon?
Yeah, well, it's solar moon. Well, if the sun were actually straight overhead, then you're totally in the shadow going straight down. But even if the sun's up here, you're going to be, solar noon is going to be the worst time when you're going to be seeing the most shadow coming out under the instrument. If the sun was at 60 degrees, that shadow area would be thinner and you'd be better off. Okay, so it's a significant thing. So then people have gone to below surface techniques. A lot of papers published on that. And there was a big paper by Hooker almost 20 years ago where they looked at all of these different geometries and techniques and ways of putting things and, you know, compared them all. So this is the sort of thing you might have on a mooring, or you've got a profiler. So they looked at all of this kind of stuff, modeled everything, And the bottom line is you can get pretty good agreement. So here's a water leaving radiance by one of their particular in-water methods. And here it is with all the different techniques. It was pretty much a straight line, you know, reasonable fit. Well, I guess that's the only one that showed it. So anyway, these in-water and above water techniques will give you the same answer, but it often takes a lot of effort, either removing surface reflectance or figuring out how to extrapolate upward and how to account for shadowing effects and whatever else was going on, reflection off the side of the boat or whatever. But you can get good agreement, but it's not something you just go put the instrument in the water, bang, you get numbers out and away you go. It's a tough problem. And that's what you guys learn in this class, is just how hard it is to get good data, whatever the measurement is. Okay, so now rest of the morning is to talk about this atmospheric correction problem. So basically just set that up for you, and then tomorrow we'll solve the problem. So here's the atmosphere. We've got a satellite up here, or maybe an airplane. It's measuring the total radiance that's coming up out of the atmosphere. Part of that's from the atmosphere, part of it's from the water. So you think of all the things that can happen. Well, here's sunlight coming in. It's scattered by the atmosphere and goes up to my sensor. That's Rayleigh scattering. So here's a single scatter. Here's light that comes in, scattered by an oxygen molecule, comes over, gets scattered by a nitrogen molecule, goes up to my sensor. That's multiple Rayleigh scattering. Here the green line comes in. There's a bunch of aerosols down by the surface, which over the ocean are usually sea salt particles. They scatter, light comes up in here. There's light that comes down, hits the sea surface, gets reflected back. There's light from this cloud, might actually come down, get reflected back up, or light reflected off the cloud would be scattered by the atmosphere and go back up. And there's light that maybe got scattered off an aerosol, then went over and got scattered by an air molecule, or vice versa, and got up. So that's called the Rayleigh aerosol term. And then finally, there's a little bit of radiance that's actually coming out of the water and making up to my satellite. And that's the part I'm interested in. All the rest of this is noise, unless you're an atmospheric optics person, in which case all of this is signal, and that's your noise. And there's white caps, of course, reflecting off of some little white bit of foam there, which is much, much brighter than the surrounding water. Okay, so I'll show you some example calculations here that are generated by a coupled version of ModTran and Hydrolite. ModTran is an atmospheric model that basically does for the atmosphere what Hydrolite does underwater. And so what I did was I ran ModTran for particular atmospheric conditions, sun angle, and so on. I generated a radiance distribution onto the sea surface. I took that radiance distribution as input to Hydrolite, solved the underwater light field and the radiance leaving the sea surface. Then I took the water leaving radiance and I propagated that back through the atmosphere with ModTran. And then I got what I measured at the satellite, but now I know all the little pieces in between. Interesting story there, I'll spend 30 seconds on. So I once wrote a proposal to NASA and I said, you know, it'd be really useful if we hooked Hydrolite and ModTran together. Well, this was rejected with the comment of one of the reviewers that it's Mobley's attempt to get the taxpayers to pay for another commercial product. Proposal not funded. Okay, then I went to the Air Force and I said, hey, we could hook Hydrolite and ModTran together, and the Air Force developed ModTran. Well, they said, well, we already have ModTran and we don't care what's going on underwater. So nice idea, but we don't need it. So it wasn't funded. So I just forgot about it. Then one day I get a phone call from Northrop Grumman, who's developing the VIR sensor. And they said, hey, Kurt, you know, you ever think about hooking ModTran and Hydrolite together? And I said, well, yeah, as a matter of fact, And so they said, well, how about we pay you to do it and it'll be proprietary to Northrop Grumman. So I said, fine, you're paying it. You know, signed a non-disclosure agreement. I got the money, hooked the codes together. They got the code, and I'm not allowed to tell you how I hooked it together, but I can show you the output. Then I get NASA saying, we're going to build this Hesperian instrument. It'd be really nice if we had a coupled hydrolyte Modtran code. And I said, you had your chance 10 years ago. I'll do some runs for you, but that's it. So anyway, there's a lot of stories like that, and you will have your own set after you've spent 20 years having proposals rejected and then funded somewhere else to do the same thing. It's just a part of science. And then a later NASA program manager said, oh my God, I would have funded that in a second. Well, didn't do me any good. Okay, so what I did was I ran Modtran with typical atmospheric conditions, mid-latitude summer, marine aerosol, sun at 50 degrees, cloudless skies, blah, blah, blah. And then I ran hydrolyte for homogeneous infilling deep water, case 1 or 2. You'll learn about these models. Here I used some chlorophyll of 1, and sometimes I added some mineral particles, and I did these simulations. And here's what you see. So if we put our sensor right at the sea surface, looking downward, then here's the total at sensor radiance. Water was chlorophyll of 0.1. Here's how much the green is the water leaving radiance, and the blue is the surface reflected radiance. And then the red is the atmospheric contribution. Well, there isn't any atmosphere because I'm right at the sea surface. But you can see that for this geometry, et cetera, that the water leaving radiance and the surface reflected parts, they're kind of the same, you know, factor of 2 difference. And this, of course, is what you measure. Notice for chlorophyll of 1, case 1 water, the water leaving radiance has gone to 0 beyond 720 or so. Okay, so like I say, that's what you measure. That's what you want. There's your surface reflected skylight, and there's no atmosphere or no atmospheric contribution. Now let's do the same thing for case 2 water. So I threw in some mineral particles, and here now, whoops, here's the total, here's the surface reflected, here's the water leaving radiance, and of course there's still no atmospheric part. But notice now, with scattering mineral particles in the water leaving radiance is not 0 out beyond 700. Okay, we're going to see a lot more of that tomorrow.
Why does the surface reflected go so much?
Say again.
Why does the surface reflected go so much?
Because I think it's a different scale. So here's 0.005. So here, surface reflectance is like 0.002, and here's 0.002. So it's just a different scale. The light field was a lot darker, so I changed the scale just to see it better. But yeah, good question. Okay, so now let's go up to 3,000 meters elevation. Typical altitude where an aircraft would fly. Well, now here's the total. Here is the surface reflected. Here's the water leaving part. But now we have a big contribution by the atmosphere just in the 3,000 meters. So I'm going to measure this, and some way I have to get rid of the red curve and the blue curve and end up with the green curve. That's the atmospheric correction problem. Here's the same thing, the total atmospheric, the at-sensor radiances as a function of elevation of the sensor. So at the surface, here we are down here, and you know, here's 1,000 meters, 3,000 meters, blah, blah, blah. And once you're up to 30,000 meters elevation, you're essentially in outer space. So that's where things like U-2 spy planes fly. Most atmospheric airborne remote sensing is somewhere between 3,000 meters or maybe 10,000 if it's something like a U-2, whatever that Avarice sensor flies on a U-2. they may be at 10,000 meters. But either way, you have a very significant amount of atmosphere that you have to correct for. Okay, another way to look at this is for these high Sperry guys. Incidentally, I wrote a proposal to the high Sperry thing saying, I have this code, I'll do all these simulations for you and help you, design the high Sperry instrument. And that wasn't funded. And literally a month later, I got a phone call from JPL, who's in on the deal, saying, hey, would you do a bunch of free simulations for us? And I said, no, because I wrote a proposal to do exactly what you're asking me to do. And it's going to cost you $30,000 for these proposals. So JPL had to cough up the money. Anyway, so they gave me all the orbital parameters for this proposed high Sperry instrument, where it's going to go, on speeds and sun angles and all of this kind of stuff. So I feed all of this into ModTrans so it gets all the right atmospheric stuff. And here's an example for Station Holoa, which is near Hawaii, 10 meter per second wind, clear sky, viewing direction of 30 degrees west. So the high Sperry is coming along and it's going from north to south. So let's say it's morning, that's morning. So there's the sun coming up in the east. High Sperry is flying north to south. So you don't want to look towards the sun. So you look 30 degrees west so you don't get the surface reflectance. So I feed all of that stuff in. So that's why it says viewing direction 30 degrees west for whatever all these atmospheric conditions and so forth were. So here's what you see. The total radiance is 1. The atmospheric contribution is this yellowish thing. That's like back in the 400, 500 nanometer range. That's 80 or 90% of your total signal is just coming from the atmosphere. Now, of that part, the Rayleigh scattering, which goes like 1 over wavelength to the 4th, something like 75% or 70% of my total signal back around 400 is just Rayleigh scattering by the atmosphere. Then there's an aerosol contribution, which is this gray line. Well, that's like 15% up to, let's say 700, like 50%. So as much as half of my signal is due to aerosols, half of it or more is due to Rayleigh. Here's the surface reflected radiance. And then finally down here is the water leaving radiance. So some way I have to compute and remove all of these things from the top of the atmosphere measurement in order to end up with this little thing here, which is at most 10% of the signal. And that's a big, big problem. So here's a bunch of different simulations for high Sperry. So we're looking at native direction, 30 degrees east, 30 west, clear sky, hazy sky, level surface, wind speed, et cetera, et cetera. You can get any of these as the top of the atmosphere measurement. Boom, your satellite goes over, it says, I measured it, here it is. And you don't know what the aerosol concentrations were and all of that. You have to some magic way, figure out how to take any one of these curves and come up with the green curve for water leaving radiance. Not a simple problem. Okay, here's another view of kind of the same thing, just plotted differently. This axis is radiance here, and this is the irradiance that you would have to divide into the radiance to get a remote sensing reflectance. So here, you notice the solid line, I think somewhere here, I said the solid line is top of the atmosphere and the dashed line is what you would measure at the surface. So for example, ED is purple. There's your top of the atmosphere irradiance, and then these dashed lines are the sea surface irradiance. And what's missing in here, like this gap, this gap, this gap, those are bands where there's strong absorption by water vapor or oxygen or whatever. There's, like if you look at the water leaving radiance, the at surface value is the dashed line. Yeah, I said TOA is solid, surface is dashed. So the water leaving radiance at the surface is a little bigger than the water leaving radiance that made it through to the top of the atmosphere. Well, that's because some of that light was absorbed along the way, some was scattered out. And so that's just the way the business works. And yeah, here's now the same thing. This is plotted as radiances, but then if you take the radiance divided by year radiance, and NASA always, NASA turns this into a non-dimensional reflectance, which is radiance divided by year radiance times pi, which is units of radiance. So NASA does all of their work now with reflectances rather than radiances. So they're using AOP rather than a radiometric variable. So here's the same thing we just saw, but plotted as in terms of reflectances. And once again, here's our water leaving part. Here's the total. Here's the aerosol part, you know, et cetera. And then these fans here are sucked out by the atmosphere. Okay, so that's the world of ocean remote sensing. And I had infinite grief from atmospheric people who say, we just don't understand what your problem is. You guys spend all this money to just remote sense the ocean. We don't have to do all that. We're in good shape. You guys just don't know what you're doing. Well, here's their problem. Terrestrial remote sensing, first of all, the land is a lot brighter than the ocean. Typical land surface, like the gravel out there, that's probably 30 or 40% reflectance versus 2% for the ocean. So you have a very bright land reflectance. So the atmospheric contribution is percentage-wise less. And then all they want to do sometimes, if you're a military guy, is you want to fly over. So look, there's some buildings, and there's where Kurt grew up in Canyon, Texas. So drop the bomb there. They don't even have to do an atmospheric correction to solve that problem. And then maybe a lot of what they do is what's called thematic mapping. They fly over and they just want to know, oh, this is pavement, that's a tree, that's bare dirt, that's a building. So at most, they will do a Rayleigh correction. And you can come up with all kinds of algorithms that will do an extremely good job of identifying water versus soil versus a wheat field versus a forest versus a building top. And they're done. So, and they get great results. And I actually had a paper one time. It was on a shallow water remote sensing paper, and it was reviewed, and the reviewer said, this whole thing is completely wrong. He must use the Mahalanobis metric to do this retrieval. Well, I never heard of the Mahalanobis metric. So anyway, paper rejected, no possibility of review or resubmission, because this one reviewer just said, it's totally wrong. Well, I went up, I dug into this Mahalanobis metric thing, and it's a way that terrestrial people use to remove correlations from one wavelength to the next. And I wasn't doing that. So the paper was wrong. And it turns out I actually then wrote a whole section on the Ocean Optics web book to show why the Mahalanobis metric does not work for the ocean. They don't have the problem of having to get rid of the atmosphere, get through the water, and then remotely sense something in a water body. They're only interested in surface properties. So anyway, end of that paper, I think I resubmitted it somewhere else, got a different reviewer who liked it. But that's why terrestrial remote sensing is generally much easier than ocean remote sensing. We picked the hardest possible problem we could. And, you know, we're interested in retrieving in-water properties like CNOM or chlorophyll or whatever, bottom properties, how deep the water is, what's on the bottom. And we have complications like surface glint, and the terrestrial people just don't have any of those problems. Okay, so I got invited to a Montran conference one time, and they said, hey, Kurt, why don't you come and tell us all about your problems in atmospheric correction, and we'll fix you up and solve your problem for you, because we're the atmospheric gurus and we understand all this stuff. So I went and I gave them a talk. It's kind of what you'll see tomorrow. And I said, you know, here's the level of accuracy that I need to do ocean color remote sensing. And the great guru of the field, who's a great guy, we're buddies and all that, he said, quote, Kurt, you'll never be able to do that. You know, I'm telling you, we need like, you know, % accuracy here. He said, you'll never be able to do that. And my response is, the man who says something cannot be done is often interrupted by someone doing it. That's an old saying. The modern version, which I like better, is the man who simply says something cannot be done is often interrupted by a woman doing it. So anyway, NASA's doing this, and it works pretty darn well, and we'll see how NASA does it tomorrow. Okay, so you have to have something to do when the weather's too bad to go kayaking. And I've always been a woodworker. So it started out when I was a postdoc. I didn't have any money to buy furniture, so I started making my own. Pretty soon the whole house was full of furniture, and then people would come over and they'd see the coffee table or whatever and say, well, can you make one of those for me? Yeah, sure. So I actually started a little company called Rainy Day Woodworks. And it was interesting that from the day I set up the company, I was just doing this on the side. I always had a job waiting before I was done with the piece I was making. Well, anyway, that's a different story. So I thought, well, I'm getting up in years now, I need a rocking chair. So I'm Googling around for like rocking chair info. And I run across this guy named Hal Taylor. Turns out Hal is like the exalted master of making wooden rocking chairs. And he has this thing, he calls it Rocking Chair University. And so you can go to Hal and you work with him for a couple of weeks in his shop, which is about the size of this room. And you will either make a rocking chair under his guidance, or you will help him make a rocking chair, depending on your level of woodworking skills. So I Googled this thing, and after the last, I guess it was 2 classes ago, he lives at the end of a dirt road up in the boondocks in the mountainous part of Western Virginia. So I go to see Hal after the class on the way home to make a rocking chair. Well, turns out, let's say Hal's a character. He is into every kind of alien invasion, government conspiracy, medical quackery thing, whatever. I hadn't been there for 30 seconds. It was like, Hal, I'm Kurt, you know, great. He says, you want to know how to cure snake bites? I said, well, yeah, sure. He said, well, a snake bites you. Go get a car battery, stick it on your arm, and electricity will kill the poison. And so I thought, this is going to be a pretty interesting couple of weeks. And, he lives in a house that he built. It's about the size of this room. It's separate from his shop. It's made out of concrete, which he built the forms, poured the concrete. The home is round. The walls are concrete. The floor is concrete. The ceilings are concrete, and there's no windows. And he's got one little corner where his bed is, and I got a bed in this other little corner. And out in the middle of the room, there's a stove and a refrigerator. So anyway, I'm thinking, well, whatever. And, you know, he's always like laying some story on you about alien invasions or whatever. And one time he comes over and he's got this picture he found on the website of this like thing with the big head and little arms, and he's got these big eyes, and he says, Kurt, look, they just found this down in Peru. And it looked like something a 10-year-old would make out of plaster of Paris, which it probably was. But to him, that was real. Well, anyway, I thought, okay, not hurting me, I didn't believe it. He's also incredibly obsessive compulsive. And what I kind of got out of this, so we went down, well, the first day I'm there, I show up at like 2 o'clock in the afternoon, And so I flew from here to DC and rented a car and drove up. And so I said, well, when you want to start tomorrow? He said, it's 2 o'clock. We will begin now and we work until it's quitting time. Well, by the end of the day, we had the seat glued up. So we went down to his wood pile and I wanted to make this out of what's called English walnut. And, you know, it's good enough for the Queen of England. It's good enough for me. So we pull out these big slabs and we start laying out, figuring out just the right grain. And I start sawing things up and away we go. And so 10 days later, I had this rocking chair. And Colin has seen it. It's just utterly spectacular. And the two of us worked. He has in his shop, for example, multiple table saws, multiple everything. And everything is set to do one cut at exactly one angle or whatever it happens to be. So he doesn't have to spend any time adjusting blades or anything like that. So he's got this checklist. It's like 10 pages and 400 steps, you know, do this, do this, do this. And so he, you know, I'd be off on the bandsaw cutting something up. He's over on the table saw and he's gluing something up and I'm routing something. And anyway, we finished the chair and just one day, all of a sudden, boom, it's done. And so it was very interesting to see how he did everything. And I remember one time, there's a rule in woodworking that you always do to one side of a board the same thing on the other side. So if you do something on one side and you don't do the other side, the board will tend to warp. Well, I had the piece that's a seat there and I was doing something on one side and I turned it over to sand the other side. And he said, no, don't do that yet. And I said, oh, okay, whatever, just turn it back over. He said, tomorrow we will turn the seat over and then you don't have to do an extra turning it over. So I thought, okay, that's the way his brain works, is you don't want to like turn this seat over twice if you can wait a day and only turn it over once. So if I made a cut somewhere here, like in some joint here, and it was off by 100th of an inch, he would make me redo it. And that's just how impulsive he was. And then I got to thinking, you know, if he weren't that way, he wouldn't make the best rocking chairs in the world. He would settle for something less. And then you'd see a little crack in the joint there, you know, the angle wouldn't be quite right. So it was really a plus in some cases that you've got a guy who's very obsessive compulsive because he makes the best rocking chairs there are. Prince Charles has one. The Sultan of Dubai brought like 3 of them. They're in museums all the way around the world. And all he's done for 30 years is make rocking chairs, wooden rocking chairs. And when I got there, he had a couple that were pretty much done. And he said, Kurt, sit in this chair. Looks at it. Well, it was kind of obviously too big. He said, well, sit in this. I sit in that. And he kind of walks around. He looks at it and he says, when you sit in this chair, are you going to have your shoes on or off? And I said, oh, well, probably be off. Be watching TV. He says, okay. He says, well, we'll start with my medium size and we'll make the legs 5/16 longer. Not a quarter, not 3/8, 5/16 of an inch. And so every chair is designed to fit a particular person at the scale of a 16th of an inch. And, you know, it fits. I spend about 3 hours a day in the chair at home, and I really wish I had it out here. So anyway, find something that's fun to do, whether it's woodworking or growing flowers or whatever, because you can't do science all the time. And if you're ever in Seattle, come by and check out the chair. Also, I have a website here, this Ann-Kurt@smugmug.com. I have all my travel pictures and everything on that website. And there's one gallery for the rocking chair. And if you go to his site here, www.haltaylor.com, you'll see a bunch of his chairs. And these things go for as much as $20,000 a chair. So they're your upper end chair, shall we say. And but anyway, check out his website. he actually links to my website and says, look what Kurt went through for Rocking Chair University. And he's on his 5th wife, understandably, and they don't even live together. And I'm thinking, like, what does this guy have that I don't have? Because I could barely find one wife. He's gotten 5 of them. He's crazy as can be. But also, one of the chairs that he was finishing while I was there, which would normally sell for $6,000 or $8,000, he was giving to a charity auction to raise money for orphans in Syria. You know, he's that kind of guy. The money's just not that important. He has to live, but he gives away about as much stuff to charity as he seems to charge people for. So he's a really nice guy. And I now know how to cure snake bites. So you get bit, come and get me. We'll get a Manual's car battery, and we'll fix you up. So that's it. So for the lab today, hydrolyte lab, do we want to start at 1 o'clock, 1:30? Do you guys have a preference? Okay, well, the sooner we start, the sooner we get it over with, I guess. What time is it now? It's probably, yeah, so it's coming up 11:45 now. Let's just start at 1 o'clock in here and away we'll go. Okay. We'll do the hydrolyte lab in here.
Yeah, yeah.
That's why I have to.
Yeah, I don't think that's. It's fine.
Yeah. You need output.
Yeah. Yeah, yeah. 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 If it's not totally common. Oh, you mean, yeah. There might have. He usually does that pre-processing step before I do it. Together. Oh, yeah. He has a very strict. Yeah. When I was looking at some of the mentioned blow in the dark, as an idea, that could be sorry.
I didn't really fall in love with any of them. Granted, it was guitar centers, so they were all just guitars. Yeah. But the ones I knew on Craigslist and put my good side. Yeah, they I've kind of gone by the mentality of like playing guitar is required to. I've got a group training meeting I'm having right now, so I get there too late. So I can get stuff for a run.
How like you can
You can also set before the yes, that would be appropriate.
there's something different. Both of these two.
It's aerosol cloud. Whereas it's really green of the light.
Yeah, I mean, man, you get like late August, it's 75, not quite close. Yeah.
Well, the easiest way is
I think it does all. I don't know. That's terrible.
Yeah, she likes it pretty well. I don't know, I think. We have this is where my
It's okay. It's okay. Sure. It's the first thing that divide.
You know, when I had this t-shirt, after it was over, and I understood what you did. And I took that video of that. And I went, wait a minute, Google. It's a replacement. Doctors got all kinds of stuff. It's their own thing.